Welcome back. Today we're doing a deep dive into, well, the sunflower. It seems simple, right? Big, yellow, faces the sun.
But there's so much more going on under the surface. It's this amazing blend of biology, math, even engineering.
Exactly. So our mission today is to unpack that. We've got the sources, and we want to reveal this hidden genius, how it connects maths, tracking the sky, and even space science.
That's the plan. We'll look at its internal clock, the incredible geometry in its head, and its history and how it even helps us clean up the environment.
Okay, let's jump in. Heliotropism, that's the fancy word for tracking the sun. Most people just assume it, physically turns towards the light.
Right, but it's more sophisticated. Research, particularly from UC Davis, shows young sunflowers don't just react, they anticipate the sun. It's run by an internal circadian clock, like ours.
An internal clock, so it knows sunrise is coming.
Pretty much. It's genetically programmed. So overnight, it doesn't just sit there. It slowly turns its head back to the east using differential growth in the stem.
Wow. So it's ready and waiting at dawn.
Exactly. Gets a head start on photosynthesis. But then, interestingly, when the sunflower matures, that clock kind of tells it to stop moving.
It stops tracking. Why?
It locks facing east. The thinking is this warms the flower head up faster in the morning, which attracts more pollinators when they first become active, more efficient for reproduction.
Okay, that's fascinating. Efficiency seems key, which I guess leads us to the next point, the structure itself. What looks like one big flower isn't right.
Not at all. It's actually a composite flower head made up of thousands of tiny individual flowers called florets. The big yellow petals, the ray florets, they're just for show, basically. Advertising.
Just attracting the bees and birds, so the real action is in the center.
Absolutely. That dense center is where the seed-producing disc florets are and how they're arranged. Well, that's where the mathematical perfection comes in.
Ah, okay, I think I know where this is going. This is the Fibonacci sequence connection, isn't it?
Bingo. If you look closely at the seed pattern, you'll see spirals swirling out from the center. There are two sets, one going clockwise, the other counterclockwise.
And the number of spirals in each direction.
They're almost always adjacent numbers in the Fibonacci sequence. Like 34 spirals one way, 55 the other, or 55 and 89. It's incredibly consistent.
But is there a reason for that? Or is it just one of nature's cool patterns?
Oh, it's absolutely functional. This arrangement, based on the golden angle, which is related to Fibonacci, is mathematically the most efficient way to pack the maximum number of seeds into that circular space with minimal gaps.
Maximum efficiency again. So it's not just beautiful, it's practical.
Highly practical. And engineers have noticed. They study this pattern for things like designing more efficient solar panel arrays or antenna layouts.
Wait, the sources mentioned NASA too, using sunflower math for space.